Hello, you're welcome back. All right, so we're actually going to continue from where we stopped. So this time around, we are looking at atmospheric pressure. Okay, so what's atmospheric pressure? Now, atmospheric pressure is the pressure exerted by surrounding atmosphere. So of course, in the atmosphere there is air. Okay, air is actually what we see around us. Okay, is the entire atmosphere is actually made up of air, and air is actually a mixture of gases, and these gases, okay, actually exert pressure, and such pressure is what is known as atmospheric pressure. Now, atmospheric pressure is measured by mercury barometer. So that means the measuring device for atmospheric pressure is mercury barometer. Okay, that's why the unit of atmospheric pressure is measured in millimeter of mercury, mmHg. Now, atmospheric pressure increases with altitude. So the higher you go, the more atmospheric pressure you get. Okay, and the diagram below shows mercury barometer. The height at which the mercury rises in that barometer is the measure of atmospheric pressure acting on it in that particular area. So now this is a diagram of mercury barometer. Okay, so mercury is actually a tube. Okay, a test tube is actually inverted in a trough of mercury, and what happens? Mercury rises into rises in that test tube. Okay, so the height to which this mercury will rise is actually a measure of the atmospheric pressure acting on that area. So one thing about atmospheric pressure is that any surface that is actually exposed to the atmosphere must always have atmospheric pressure. So anytime you have a liquid, okay, a container of liquid, of course you know very well that a container of liquid has its own pressure. Okay, it has its own pressure. So then if it is exposed to the atmosphere, that means the pressure now that's acting in that liquid, okay, the pressure of the liquid, please pardon me, the pressure of the liquid, PL, is going to be equal to the pressure, okay, due to the depth of the liquid, which of course is density multiplied by G multiplied by height, then plus the one of the atmosphere. So you have to combine. So the pressure of the liquid now is going to be combined effect of the one of the atmosphere and the pressure due to the density and the depth of the liquid. Okay, so please take note of that. All right, so now let's now talk about gas pressure. Okay, gas pressure. This is the pressure exerted by molecules of gas. So molecules of gas actually exert pressure. Of course, you can actually feel that. Okay, you can actually experiment that when you blow air on your hand. So you just excited the air around, okay, when you blow air. So you discover that you feel the pressure. Though you can't see the pressure of gas, but you can feel it, okay? When gas collects with the walls of their container and of course with each other, right, they actually exert pressure. So now the gas molecules exert pressure on mercury, causing the mercury to rise in the heart. So this, the measurement of gas pressure, we use mercury manometer. Okay, remember that of atmospheric pressure is barometer, mercury barometer, but here we use manometer. All right, so this is actually the construction, okay, or a schematic diagram of a manometer. So this is where the reservoir of the gas. This is a tap that actually where you open to let the gas enter into the U-tube, right? So when the gas enter into the U-tube, what actually happens? Okay, you discover that the gas was gonna rise, the mercury, okay, because mercury is found in between at the U-tube, is going to rise to some height. So there's going to be a difference between this height and the height of rising of the mercury at either arms. So difference between the height of mercury at either arms of the U-tube, okay, give a measure of the atmosphere, the gas pressure. But it happens that this H, okay, this particular U-tube is open at the other end. So invariably now, the total pressure of this gas, okay, or the total pressure acting on this gas is not just going to be the gas due to molecules of the gas, all right? Not going to be the pressure due to the molecules of the gas. You're also going to include the atmospheric pressure. So invariably now, okay, for gas pressure, for you to measure gas pressure, okay, so the pressure, the very first pressure you measure is the pressure due to the, of course, the height, okay, the difference in height between the two arms. That's one, okay, then plus the pressure due to the atmosphere. So that's going to be the total pressure okay, due to the difference uh, of height in the two arms, and that will give you the okay, plus the atmospheric pressure that will give you the total pressure acting on the gas. So please take note of this. So this is a note. Since the other end of the U-tube is exposed to the atmosphere, the pressure of the gas is the sum of the height of the mercury and the atmospheric pressure. So the formula I just gave you is here. So in a mercury manometer, okay, to measure the pressure of the gas, you have to actually add the height of the difference, okay, of mercury between the two arms, and of course the atmospheric pressure acting in that particular area. All right, so now we are going to be looking at the application of this atmospheric pressure. Okay, where is it actually applied? Now, atmospheric pressure is found applicable in the following devices: a siphon. Now, you must have used a siphon before. A siphon is actually a device that is used to actually transfer liquid from one part to from from two different altitude. For example, you want to suck fuel from a car into a container, right? You use a pipe to create a siphon. Right, we have syringe. Of course, you must have used this one before. Lift pump, Hess apparatus. So we discuss them one after the other. So a siphon, starting with a siphon. A siphon is used to transfer liquid from one container to another, employing the difference in the atmospheric pressure acting on the liquid placed at different altitude. Okay, so this is a typical diagram of a siphon. Okay, so one liquid, one container is at a high altitude, okay, while the other container is a lower altitude. So discover that atmospheric pressure actually is greater at higher altitude. So you discover that the atmospheric pressure at this one at the high altitude is greater than the one at the low altitude. So what happened? Then this atmospheric pressure acting on this one will force the liquid to rise through the U-tube, okay, and it's being collected at the container at the lower altitude, right? So this is a siphon, okay. So invariably, basically, people that actually transfer, let's say, fuel from a tank to another container make actually employ the use of a siphon, right? Okay, so now syringe. A syringe draws and collects liquid into a barrel container via a tiny nozzle as the piston is given an upward stroke. So of course, I'm very sure people that actually take injection, you just put this syringe inside the liquid, draw the piston, and of course that syringe we enter the liquid enters through the tiny nozzles, okay, and of course enter into the barrel of this when the piston is being lifted up. Okay, now what happens is this: as you actually draw the piston backward, you actually increase the volume of the volume of the barrel, and the atmospheric pressure acting on the liquid. Remember, the container is having atmospheric pressure. Why? Because it's exposed to the atmosphere. Will actually force liquid to enter into this barrel. So basically, just it's just an application, okay, nothing much, but there's just one. Of course, this will have a lift pump. A lift pump is a device that is used to lift water molecules from a very low altitude to a high altitude. Lift pump is okay. Lift pump as a syringe. It's like a syringe, okay, whose barrel has two valves. Now, okay, for people that have borehole, you would have to pump water before you can actually take it into your container whatsoever, okay, and you're pumping that water from the ground against gravity. So for you to do that, you actually use a lift pump, okay. So lift pump actually create atmospheric pressure, okay, difference that will cause the liquid to move from that very low altitude against gravity to a higher altitude where it is actually being collected. Okay, so much about lift pump is what you can actually go study, browse, and of course get to know how the operation. Okay, I'm only interested in the last application, which is the Hess apparatus. Okay, now Hess apparatus is used to compare the densities of two liquid. It is made up of an inverted U-tube inserted into a container containing two different liquids at the same altitude. So now, anytime you want to compare the density of two liquid, you use Hess apparatus. This Hess apparatus, there are two liquid, let's say liquid 1, liquid 2, okay, and they are at the same altitude, and there's a U-tube that's connecting them, okay. So you know very well that anytime a container is exposed to the atmosphere, atmospheric pressure must act on it. So atmospheric pressure acts on this particular liquid, and of course what happens, it rises the height to which it will rise depends on the density of this liquid, and liquid 2, okay, atmospheric pressure still act on it, and the same atmospheric pressure is acting, the same amount of atmospheric pressure that's acting on P1 on liquid 1 is what is acting on liquid 2. Why? Because they are the same altitude. Okay, so the same atmospheric pressure act on liquid 2 and it will rise. Now it is called that two of them will have different heights of rising even though they have the same atmospheric pressure. So the height to which they will rise depend on their density. Okay, so invariably now I can actually generate Hertz apparatus formula. Let's say the atmospheric pressure acting on liquid 1 is is please pardon me, is P1 or ATP1. Let me just use P1. Okay, then one acting on liquid 2 is P2. So both the atmospheric pressure on P1 is equal to the atmospheric pressure on P2, and we know that pressure is given by the formula density, okay, multiplied by height h1, then multiplied by acceleration due to gravity. The same with P2. All right, density 2, the density of actually liquid 2 multiplied by the height at which liquid 2 will rise, then multiplied by G, atmospheric pressure. So that way now we can compare the density of the two liquid. Okay, so I can just rearrange this equation, density 1 then divided by density 2. Okay, and then that's what I just did. Now I carry P2 to come to this other side of the equation as a divisor, then definitely the whole of this will go to this side as also as a divisor. So I'm going to have H2 then divided by H1G. Of course, you know that G cancels G. All right, so I now have that density of the first liquid divided by the density of the second liquid is equal to now the height of the second liquid divided by the height of the first liquid. Okay, so this relationship shows that density is inversely proportional to height. Okay, so this particular formula is a formula that we get from Hertz apparatus. So some question actually will require you applying this formula, okay, to solve the question. Okay, so now let's see how that works. Let's see if there's an example question. Okay, so look at question here. Example: two vertical capillary tubes of same diameter are lowered into a beaker situated at the same level containing liquid A and B of density. Okay, so the density of A is 9.2 times 10 raised to power 2, and the density of B is 1.30 times 10 raised to power 3 respectively. A suction pump is used to withdraw air from the top of the liquid columns in the tube by means of T-piece arrangement until the liquid in air rises to a height of 26.0. Okay, so the liquid in air rises to 26.0 cm. Calculate the height of liquid B. So once you see this question where density is being compared with height, then you know that you're applying Hertz apparatus formula. Okay, so here we go. That is the formula that we're going to apply this formula here. So now let's fix our values. Okay, first of all, let's P1 now, let's say is the density of A, right? So of course from what we have here, the density of A is 9.2 times 10 raised to power 2. 9.2 times 10 raised to power 2. And of course the density of B is 1.3 times 10 raised to power 3. 1.3 times 10 raised to power 3. Okay, now it's equal to H2. H2 is now the density of B, is the height of B, please pardon me. So height of B, that's what let's do. Okay, I believe that is that the unknown. Okay, yeah, height of B is the unknown, then divided by height of A, we are told that A rises 26 cm. So if I cross multiply now to make height of B the subject of formula, but that's what I'm looking for. All I'm gonna have is 26 times 9.2, then times 10 raised to the power of 2. Okay, then divided by 1.3 multiplied by 10 raised to the power of 3. Alright, so let's do this. 26 times 9.2 divided by 1.3. I better see. 26 times 9.2 times 100. 10 raised to the power is 100. Okay, so Let me bring the calculator here. 26 times 9.2 times 100. Okay, then divided by bracket open 1.3 times 1000 bracket close. Okay, so of course 10 to the power 3 is 1000, right? 1.3 times 1000. So everything now is gonna be 18.4 cm. So that is Hell's apparatus. So that is the applications of density, atmospheric pressure. Please pardon me. Okay, so we are going to be solving a lot of questions. We will solve a lot of questions in the next video. Okay, see you in the next video. Thank you very much.